Hello, friends. Welcome to episode 10 of Kermit GNC. Today, we will work on building an atmosphere model. So, I will go over showing you the ISA atmosphere model block, as well as we will use a 1D lookup table. So, this is the first time I will show you how you can use a lookup table. If you remember our conversation from before, when you go from building a low fidelity model towards medium fidelity, all the coefficients and the numbers are swapped with lookup tables. How do you get those lookup tables? You get those lookup tables mainly using flight data, which is a big thing to get. But industries, they collect flight data from actual flights and they use that to get their lookup tables built up. And then they use those lookup tables into the model in Simulink to make basically to increase the fidelity of the model. So we will go over that. I will show you how you can configure the 1D lookup table block inside of Simulink. And yeah, so the idea is we want to turn our dynamic pressure as a function of altitude. That's the main idea. So let's go to the model and let's start building. So we have this model we developed so far. Let's talk about some of the things today before we actually go about building the lookup table. So you have the 6-staff Euler block here. That's our brain of the model for now, right? The 6-staff Euler angle block, it uses the NED convention, NED sign convention, meaning north, east, and downwards. So for the altitude, downwards is positive, which means over here for the initial position, if I, let's say, put a 1000 for my ZE value, it means I am starting 1000 feet below the below that reference point, or you can call it the origin, or 1000 below the reference level would be a good way. And therefore, we used a -1 gain block here to swap that. So, down is not positive anymore on our scope. On our scope, it will be up is positive, right? So we swapped it. So it makes sense when we look at the scope. So that will come into play when we will design our atmosphere block. So I wrote a note over here, NED convention. If you want to use a different convention, right? Again, you can use gain blocks to change that, or we may do this later in the future, is to completely remove this 6-staff Euler block readily available from Simulink and actually build the physics that goes into this block entirely by yourself. That's another way you can do that. Next thing is, let's go into the pilot commands subsystem. On the pilot commands subsystem, we have del E, right? The elevator deflection. So here's the sign convention we are using over here in the model. Meaning, if I put a positive elevator deflection here, a positive number greater than 0, that would simulate nose down attitude for the airplane. So I'm pushing forward on my stick. And if I put a negative value, I am doing nose up attitude with my airplane, or pushing or pulling back on my stick, right? So it comes in handy to have these little notes about sign conventions, because whatever sign convention you define, you want to be consistent throughout the model, so your data would make sense when you actually try to analyze it. Okay, moving to the top level, let's build the atmosphere block, right? In order to do that, what I would do is I'm going to get an import, and let me make a subsystem out of it, because I want to have this as a subsystem so it does not get cluttered up. And then I can delete this wire for now. Let's size it properly. And I would swap this, or I mean rotate it. So Control plus R. Okay, that's better. What that will do is I am going to feed my altitude into this subsystem because, like I said, we want to design this as a function of the altitude, right? Our dynamic pressure Q bar is going to be now a function of the altitude. If you recall, if I go into the aerodynamic subsystem and then Q bar subsystem, our density in calculating Q bar was the only constant term, right? Q bar formula is 1/2 rho v squared. 1/2, that's the coefficient. V, velocity, that is being accounted for. The velocity comes from the model. But rho was the only constant we were using so far, or I should say we were assuming so far. So that will change. Now rho will not be a constant. Now rho will be a function of the altitude. So what I will do is I'll come back to this. Let's go to the subsystem, the new subsystem we created, and let's call it atmosphere. The reason I have a separate subsystem instead of just doing the changes inside the aerodynamic block is because later, if I want to put more things into this atmosphere subsystem, it will be easy to do those modifications. So double click inside. Okay, let's name this. This is our altitude. I'm going to have an output, and that output will actually give me my rho, right? Now rho is going to be a function of the altitude. So I will design it here. In the middle, I will get my 1D lookup table. If you just type 1D after double clicking on an empty spot, you will get that. And if you noticed, let me type that again. If I see there is a little description here, there is documentation. You can read documentations. That is a very good habit to read documentations. But here is the 1D lookup table. And now I'm going to go inside the 1D lookup table and I would configure this. So what I will do is there is table data and there is breakpoints or breakpoints 1. Table data, I'm going to put the values there, and I will explain a little bit how I got those values. But so what I'm doing is I'm defining my breakpoints, which is all the altitudes that I will be playing around. So it's spanning from 0 to 10,000 meters, right? If you want to add more, you can always come here and add more. But for now, I'll just stick with that. That is my breakpoints 1. Breakpoints 1 is basically your independent variable. So if you want to think of it graph-wise, it's what goes on the x-axis. And then table data is your dependent variable, which is your y-axis. So these are different rho values. So at 0 meters or at sea level, I get rho of 1.225, which was the constant we were using earlier. At 1,000, my rho is 1.112, and so on and so forth. Another way you can define this vector over here is, you can define it like that, like how we typically define vectors inside of the MATLAB environment, if you have played with that before. But you can define it. So this is basically me telling the system, okay, I want to define it from 0 to 10,000 with 1,000 intervals. I mean, not intervals, but 1,000 increments. That's the right word. So, that way you can also get it. So I'll just leave it like that for now. Let's apply. Oh, also before I apply, go to the algorithm tab. And over here, my interpolation method is linear point slope, right? So I will keep that. For extrapolation, I am going to clip it. So I want to not want it to extrapolate. I wanted to cut it at my limits from 0 on the lower end to 10,000 on the higher end. Okay, once I do the clipping, and then what I will do, I'm just going to check this box off, use last table value for inputs or inputs at or above last breakpoint. And then let's apply and okay. And you notice after I put the data points, the graph is actually, or the plot is actually shown here in this little block. That is a very cool feature Simulink has. That way you can visually see your plot. And, if you have taken these data points from like an Excel spreadsheet or something, you can verify that you see the same plot that you have on the Excel spreadsheet, something like that. Okay, I'll put this one here. For the altitude, I'm going to put a saturation block because I do not want to have wonky altitudes configured. So, it just is a critical parameter. Makes sense to have a limit there. Okay, 0 to 10,000, right? That is the 1D lookup table. Let's go back up to the top level. And now you see it feeds in altitude and then it gives out a row to you. And this row now is a function of altitude. I will collect this. So using my go to block, let's rotate it. And then I will name it. Let me use a capital R to have a differentiation, make the visibility global. Okay. Now this row should feed into all of my system downstream, which means going into the aerodynamic subsystem, back into the Q-bar subsystem, I will remove the constant row off of this now. And then let me use a from block. And then I will get my capital R row over here. And then this can go away as well. There goes that. So that way you configured your row to be a 1D lookup table and not a constant anymore. And this is mainly slowly what you will see going towards medium fidelity is, you will go and replace all the relevant constants, which, we are going to talk about it later, all the relevant constants one by one with lookup tables. Lookup tables would come from real flight data. Things like, CL alpha, for instance, CLO, all these will become a function of some other variable or maybe multiple variables. That's where you increase fidelity, right? So going into swapping the row everywhere. So for the aerodynamic block set, I think that was the only row inside. For the moment moment subsystem, let's go and make sure we have used the right row wherever it needed to be used. So right now, this elevator trim is not the equilibrium algorithm. This is the trim wheel algorithm. And if you remember, we are not using this for now. We have it in place if we want to build up on that later, build up a trim wheel system. But for now, we are not using it. Still, let's go inside. Make sure we are not using a row from block. Okay, nothing there. CN subsystem. Do you see a from block that has row in it? I do not see any. Let's get out and then CL subsystem. This looks clear. And again, nothing to worry if you accidentally miss finding one. I am sure the system is going to throw an error message at you when you would try to run it. But I know inside the trim equilibrium solver, we had row defined, which was here, if you remember. So this row can be changed. Let me double click. Looks like it's not liking the single click. Okay. All right. That one is swapped. And then the lateral residual loop also had a row right there. So double click, swap. Nice. And I think everything else over here is good. Okay. And then, yeah, looks like it's all configured for us now. And what we can do is we can get rid of this scope now because, We have used the scope in the previous episode to verify our equilibrium solver. So, if we need it, we'll bring it back up. But for the sake of keeping enough space and everything, okay, there goes that. I will put, so I do have my Euler angles scope here, and I also have my altitude scope here, right? So we can do some checks. Now, the first check that would be useful to do is go inside of this atmosphere subsystem, put a scope on the outside right there, and also put a scope on the inside so you can see what altitude you would feed, and then you can see what altitude, what row you would get. We can use that to verify that we did the system design right. So let's go into the 6-stuff Euler block. Let's make sure that we have all zeros everywhere, so we are not feeding any irrelevant numbers, right? So all of these are initial values are all 0. These can stay for now, but then these are important. So those are 0. And let's go into the pilot commands and let's make sure all these guys are 0. So throttle 0, del E, del R, del A, all of them are 0. What I would do is run the simulation for maybe 2 seconds. And then go inside. Let's open the scopes. Okay, so there are 2 of the scopes if you notice. This is the inside altitude and this is your row. Now I would look at the initial point. So check this out. The altitude is at 0 and it is giving 1.225 in the beginning. Don't worry about what's happening later, but all you want to see is, okay, if you feed 0, you're getting 1.225, which is the value, right? Now, let's do the same thing with 1,000, right? So let's go all the way out. Over here for my initial altitude, let me put like a 1,000. So now remember, if I want to put 1,000, I want to do negative 1,000 here because this follows the NED convention. That's what I was talking about. When I say negative 1,000, it means I am starting at 1,000 feet above the origin level or reference level, however you want to think of this. Okay, so now let's run that again. All right, now if I can see, if I have 1,000 for my altitude, my value is 1.112. And if you remember, it matches. This is the value we had defined inside of our 1D lookup table. Let's open that up. So if the altitude is 1,000, you have 1.112. Right? So that way you verified that your system is behaving as expected. So that's a good thing. Now you can get rid of the scopes once you are done verifying. And let's go up here. A couple of things I want to talk about is how did I get those values to put inside of the lookup tables, right? So these values, if you just Google, I actually typed the international, let me think what it was, ISA values. Basically these, if you remember, I showed you this ISA atmosphere model block. So this is how it is calculated using the ISA model. It is the International Standard Atmosphere, ISA, International Standard Atmosphere, and it is a standard. So there is a standard that is being used to get all these values. Having said that, what you can do is you can Google ISA atmosphere table. If you do ISA atmosphere table, let me actually show you what you will get. So if I do ISA atmosphere table, or you can do calculator, table, different row to altitude, and you can see that these are the values that we put around the same ballpark, right? At sea level 0 meters, density is 1.225. At 1,000 meters, it is 1.1116, so on and so forth, which is matching to what we have. Another way is you can read into how they have defined these standards, right? How the formulas have come. They actually use like a set of formulas to get the standards built up. If I want to show you, let me give you a quick glimpse. So they get the temperature using that formula, and then those are the values, predefined values. And then they get pressure, and then they use ideal gas law to get density. So ideal gas law, PV equals nRT. So here is the full picture. They find the temperature, then they find the pressure, and then this is the ideal gas law, which helps them to find the new rho. And the rho 0 at sea level is considered to be 1.225. So this formula is used. Now you may ask a question as to why use a lookup table when there is a formula that we can design inside Simulink, like we have designed other formulas. That's a very good question, valid question. The reason we are using a lookup table is to make it faster, easier to debug, easier to visualize, and essentially have, identical inaccuracy. But having said that, I would not rule out the other option. Yes, you can absolutely design the whole formula way of doing it. Now, however, for this application, you can do that. But imagine, lookup tables are used from, like I said, real flight data, right? And when that is the case, not for this specific Q bar calculation, but for other stability derivatives, control derivatives, things like that, there is only flight data, right? I mean, if you do the formula way, it can only get you so far. But the real flight data is what you want to emulate, which is why there is no option of doing formulas there. You want to learn how to do lookup tables there. So, which is why I use this to give you a little, glimpse of how it is used. This is a 1D lookup table, but there are others too. There are like 2D lookup tables. There are multi-dimensional lookup tables, like you can see over here, 2D, 3D, ND, and, other types as well. And that's where the fidelity increases with these. There will be, like, when you go towards high fidelity modeling, you would be using like ND lookup tables at multiple places. As I have told you before, when the flight simulation engineers, when the GNC engineers, they design these to have a flight simulator, there are like tens of thousands of stability control derivatives hovering around. And so you can imagine, if they have lookup tables for all those, then how many lookup tables there will be. But at that scale, you can also imagine how easier it would be to debug, troubleshoot when you have issues if you have lookup tables, right? So hopefully you are convinced to see the importance of the lookup table. However, if I did not use a lookup table over here for the atmosphere, what I could also do is I could type ISA atmosphere model. There is a block that is already configured for this application. You can also use that. That is another option. Let me rotate that. So this block can also take in your altitude. H is in meters, and your altitude uses the ISA standard. And then if I double click, it gives out temperature in kelvins, A, meters per second, velocity, P, pressure, and then rho, density. Again, you can take density from this and then just ignore the rest of the three for now. Like I said, that is why we have a subsystem, so we can build up more on this later. There are parameters. If this is inside double clicking ISA atmosphere model, you have, use extended ISA model, and then those kind of things. You have change atmospheric parameters. You can change your default values here. So the calculations, if for whatever case, if you want to change it, and then you can use your output kinematic and dynamic viscosity. So you can also get those as well if you would want them, right? Yeah, so that is the ISA lookup atmosphere model, but I'm going to stay away from that for our experiment or for our modeling purpose. I will just have the lookup table there. So, we get we get on the right trajectory towards medium fidelity slowly and slowly. So that was all I had. And after this, you are at a good spot where, if you want, you can play with pilot commands. So if you double click on the Euler angles, this is a good one to watch. And then, you can put this on one side and you can make the timer to be infinity. And when you are gonna change your pilot command real time, I would like to have simulation pacing, because then I can see my pacing properly. I have covered why you want to have simulation pacing in one of the previous episodes. Again, if you haven't checked those out, the description has links to them. And so that is that. And then I will bring this to this other side, go into the pilot commands, and let's see. I can run this. The model is going to take a little time to achieve equilibrium. And you only want to do the changes once the equilibrium is achieved. So here you go. It looks like it is pretty still dropping down, but pretty close to the equilibrium. But once it is stable like that, you can start putting pilot commands. Like if I want to do like elevator del E, let me put like a 3 degrees nose down. So you saw the pitch angle went downwards like that. And then you can give it a few more minutes, or sorry, seconds, for it to achieve equilibrium with the new pilot command. And once we will see stability, where it's not dropping anymore. Okay, it jumped up, but then let's see if I want to give it -1, pitch up, and then it's gonna go up. It may have hit one of those limits, but let me stop that. Let's see what it did. Okay, looks like it did that profiling. And again, it is doing what we are expecting it, right? When I had a positive elevator deflection, it went down on the pitch angle. When I had a negative deflection, it went up. All the weird behavior, I'm sure it is because, the equilibrium values, if you remember, we must put these equilibrium initial conditions or values onto our 6-staff block here to make sure that we are starting pretty close to the equilibrium. But that's not a big deal. The main idea is that my simulator, the flight simulator model, is behaving as I would expect it to be. So far it's looking good. Majority of the modeling gets done here. And yeah, I will see you in the next episode. Until then, happy modeling.